polygons. So in computer graphics, in 3D computer graphics, all that we see is made out of polygons. It's made out of geometry somehow. So if you see like Geralt of Rivia in the Witcher games, then he's made out of a bunch of triangles, basically. So anything we want to represent, it needs to be defined as geometry. Geometry defines the 3D objects in the scene. So on this picture, we see this cube. It's a bit messy, but you can see it's a cube, right? So a cube would usually have 6 faces, but in computer graphics we define it as this set of 12 triangles, 12 faces. And you might think, okay, why do we need these triangles? And I'll explain to you in a moment. But the way you would represent a cube would be to define these 12 triangles. And there is actually this practice session task where you will construct such a cube out of 12 triangles. But in the end, when whatever the object is it a cube, is it Geralt of Rivia, then it is made out of a bunch of triangles. And the GPU is parsing these triangles and projecting them to your flat screen and shading them. But let's not jump too much forward. First, let's talk about these triangles. So, some very useful scientific facts about triangles. So there's a bunny again made out of triangles for rendering. Triangle vertices always form a plane. And this is why you don't want to have like other polygons. Because as soon as you have like 4 vertices, you could pull one of the vertices, you could define one of these vertices as being outside of this plane defined by the other 3. So there's only this very, very constrained case where they're all 4 on the same plane and you have this very nice polygon. But as soon as one of them is not planar with the others, then it's hard to define what happens. Like, is there an edge that kind of folds this polygon? Does it have to be somehow curved, or like how would you render it? Like, it would be hard to define there. But if you have only triangles, they're always on a plane. If like with other shapes, you could have this degenerate geometry that's kind of ill-defined. So you don't want that. You want triangles. They're always planar. You cannot go wrong with triangles. Furthermore, every other polygon, or let's say a simple polygon, can be converted to triangles. So if you have a square, you can draw its diagonal and you have 2 triangles. If you have another more complicated polygon, you could split it up into a bunch of triangles. Triangles are also easy to rasterize. So this rasterization, this is one of the steps in the pipeline, if you remember. And don't worry too much about it. It's basically just that your screen, the monitor that you're looking at this video from, it's a grid of pixels. So you have a bunch of pixels there, a bunch of rectangular cells. They're very small, very tightly packed, but in the end of the day, it's still just a grid. And rasterization just means that if you now have a triangle in this perfect mathematical space, and you want to show it on your grid of pixels, then which of these pixels need to light up so that it would show the triangle as accurately as it can. And for triangles, it's easy to calculate like how which pixels are in the triangle and you should color, and which are outside and you shouldn't. And there's a practice session tasks, actually several of them, that have these rasterization algorithms that you can implement. Now, triangles are also convex and simple, and we'll see what those 2 terms mean in a moment. 3 vertices, any 3 vertices you have, always form a convex and simple triangle. So you could send to the GPU any 3 coordinates and you might not even think like, is it a triangle? Like, how is it planar? I don't know. It's just three coordinates in 3D space, and whatever they are, they form a triangle. So these are some very useful scientific facts about triangles, which a lot of you probably knew from your high school math class as well, but it's good to repeat those every now and then. Now, what are these different terms that we used? So convex polygon. It's also in Estonian, it's called kumer hulknurk. So this is how you learn it in your Estonian math class probably. So there are some definitions, and there's several definitions, but they're basically equivalent. The first definition would be all convex combinations of the vertices are inside the polygon. We learned about convex combinations before. So if you take these bunch of vertices and you have the convex combinations of the vertices, and you put in any real numbers that satisfy the convex combination criteria. If you remember them, there are two criteria. The sum needs to equal to 1, and all of them must be non-negative. Then all the numbers you put there must be the inner points of the polygon. They must all give points in the polygon. But maybe this is hard to test and hard to visualize, so let's see some other definitions. Straight paths to all vertices from any point inside the polygon are also inside the polygon. So if you have a shape, you have some vertices. So if you can find a point inside that polygon where if you draw a line from that point to some vertex, and this line is now partially outside of the polygon, then it's not a convex polygon. Now that's kind of this contra example where if you want to test if something is not convex, because for all the convex polygons, all the straight paths to all vertices from any point to the polygon are also inside the polygon. Any point you take, draw paths to vertices, all these paths must be inside. The polygon is equal to its convex hull. So this is very similar to actually the first definition. So a convex hull would be the shape you get if you take all the convex combinations of the vertices, all the points. But this is a bit different definition. So all the interior angles are less than 180 degrees. So if you have an angle, and let's say your shape is like this, if all the interior angles are less than 180, then it's good. But as soon as you have like an angle like that, that's larger than 180, an interior angle, then you're not good. We'll test these things on actual polygons in a moment as well. So these four definitions. And here are some examples, so convex examples, and the other ones that are not convex are called concave, nõgus hulknurk. So let's look at these convex ones. Well, triangle, we already saw that all the triangles are always convex, so that's a bit boring example, but let's look at this one. So all the interior angles are less than 180. So over here, the angle ADC, well, this is less than 180. BCD, that is less than 180. ABC, yes, it's less. And BAD is also less. So all the interior angles, these ones, are less than 180. So this is a convex polygon. We can look at this example on the far right. So here we can find an angle BCD. And if you look at the interior angle of this angle here, then this is larger than 180. So that would not be a convex polygon. It's concave. If we take like the second definition, so if we put a point over here and we draw a straight line to D, then this line would go outside of the polygon. So that's not convex due to that definition either. And then they're all equivalent, so it would suffice to just test one of them. If you take all the convex combination, if you want a convex hull of this polygon, then that would just basically be this shape that would connect B and D as well. So it would be a triangle, ABD would be the convex hull of this particular polygon that would that would also result from all the convex combinations of these vertices. Now we also saw these other definitions of simple polygon, lihtne hulknurk. So this just means that there are no intersecting edges. So on the left we have a simple polygon, all the edges are very simple, they're not intersecting, but we could also define these edges like that. So this is non-simple, so it's hard to say what is happening with this polygon. So what is happening here? Is it like twisted, or is it two triangles, or like how would this happen, or what would this mean, or is it some kind of a curve that is inside there? Like if you would take a piece of paper and you would twist it, then it would curve. So that would be non-simple. In computer graphics, we usually want to deal with simple polygons and well, usually triangles. But if they're not triangles, then simple is a good requirement, and then convex is usually a good requirement, because there are certain algorithms that work well on convex polygons. Now let's look at some triangle structures. Now these are structures that you can make out of triangles that are supported by OpenShell, basically. So the first thing is you could just define a bunch of triangles. You could define these vertices A, B, C. So this is a counterclockwise orientation. So here we're seeing the front face of this ABC triangle. D, E, F, again front face. G, H, Y, front face. So we have three triangles. We can send to the GPU the coordinates of A, B, C, D, E, F, G, H, and I. So if we send those coordinates to the GPU through an API, and we say that these are triangles, then the GPU is going to render us these three triangles, and that's what it will do. Now we can actually create, or people have created, more interesting structures that will allow you to make connected surface of triangles. And one of these would be a triangle strip. So notice here, we are sending to the GPU exactly the same amount of data, the same 9 vertices, so 9 times 3 real numbers, because there are three-dimensional space, there are 3 coordinates for each of the vertices. But we say that these coordinates now denote the triangle strip, not triangles, but a triangle strip. And then it will render these triangles to you. And they are also, these triangles will be connected to each other. So the first one would be here, but as soon as the fourth coordinate D comes, then it will make a new triangle with these 2 previous vertices as well. And if you send like another vertex, it will make a new triangle with 2 of the previous vertices. And another vertex, a new triangle with 2 previous vertices. And this will all be like front facing you, because well, it is a bit tricky because some of these will be now clockwise ordered, because this is just how this strip would come to be. But yes, you can make a larger surface with of connected triangles by saying that these 9 coordinates are now part of a triangle strip. The third thing you can do is a triangle fan. So again, we have the same 9 coordinates, but now we say that these 9 coordinates define a triangle fan. And this would create you this surface where the first coordinate is kind of in this middle point, and then the new vertices form triangles with the first vertex and the previous one. So ABC, it would be one triangle. Then if we send in D, then it would take C and the first one form a triangle. If we send in E, it would take D and the first one A form a triangle, and so on. So it would create this kind of a fan surface or a fan structure. So from this video, you should now understand more about triangles. They're planar, they're simple, they're convex. They're easy to rasterize. And other polygons can be also made into triangles. You should also know more about polygons, or reminded yourself that what are convex and concave polygons, and this definition of a simple polygon. And lastly, we saw some triangle structures, just separate triangles, a triangle strip and a triangle fan.